And in our last and final lecture, a little discussion about equilibrium, which is really in reference to that double arrow. Okay, I do want to add a little layer here just for organic chemistry. If you see anybody reference this as an equilibrium arrow, feel free to yell at them and tell them that they have no clue what they're talking about and they should go talk to a chemist. If they are a chemist, you should tell them to go talk to a better chemist. So there's our equilibrium reaction. Okay, we have both a forward reaction and a reverse reaction. This is known as equilibrium. The equilibrium concept itself is extremely complicated. There's a lot of math that can go behind it. It is so kind of important and broad as a topic that Chem 152, second semester general chemistry, spends probably half of the semester just looking at the equilibrium concept and varying application rules. Okay. The big piece that also gets tied to equilibrium is this concept of Le Chatelier. Le Chatelier's principle says that our reactions will always get to an equilibrium. And once they are at an equilibrium, they will do whatever it takes to maintain that. Okay. This can be seen with humans. If you try and stand on one foot, okay, you will notice that you might wobble a little bit. For those jackholes that have really good balance, okay, get a friend to come up to you and push you while you're trying to stand on one foot. That friend is trying to mess with your equilibrium. Okay? So what happens when they push you is that you will wobble and you will try and maintain that equilibrium to get that extreme vertical aspect. So you may wobble left and right to kind of counterbalance and reobtain that equilibrium. If you had a horrible sense of equilibrium, you're probably falling all of the time because you don't know where that balance is. Okay? Chemical reactions have a great sense of equilibrium and they will always move to get to that equilibrium. Okay? The speed at which they do it is an entirely different question, and we'll sort of address that in a little bit. Okay? But what we're looking at is how we achieve that balance. So there are two kind of comparisons that we can use to address equilibrium and the Le Chatelier's principle. If we go through and take a look at a seesaw, which appear to be making a comeback, so now maybe people know what's going on with these, is we've got a fulcrum in the middle. That fulcrum is what I'm going to call my equilibrium. Okay, that is my equilibrium fulcrum. It is what's going to dictate how my reaction runs. I then also have these two boxes that I can place on them. Okay, there's a reactant box and there is a product box. If I am at equilibrium right now, the reactant box and the product box are the exact same weight, and we actually have kind of a boring seesaw. It doesn't move. Okay, and this becomes the problem with this example, and we'll address that in a little bit. So, we've now achieved equilibrium. So what does Le Chatelier say happens? Well, Le Chatelier comes along and says, okay, let's mess with it. Instead of it being completely even, I'm now going to add another box to the reactant side. So now I'm going to have more reactants. Okay, well now what happens? Okay, the reaction, remember our reaction is reactants and products, needs to counterbalance that so that it can balance out and make sure we have the same amounts on each side. So for those of you saying, well, I just put another box here, what you're now doing is adding something to the system. The whole point of equilibrium is that the chemistry, the reaction has to do that on its own. To make those products, they have to come from somewhere. Those products would have to come from the reactants. So if you're going to say, I want to put on this whole new box, what does that mean on the reactant side? Well, that means I'd have to get rid of that box on the reactant side, which would mean you're still out of balance, so you screwed up. Okay, so what's going to happen is now the products have too much, so we're going to have to shift our balance to form some reactants. And so what will end up happening is we will cut maybe half of that box out, and we will convert that other half into reactants. And now we have re-achieved the equilibrium. Okay, that's the point of equilibrium. We're just trying to maintain that even keel, that level setting. Okay, that's the point. Okay, are there other things that we could do to mess with the equilibrium? Well, of course, I could come through and be like, well, I wanted products, so as products are made, I'm going to remove them. So if I come through and now remove those products, well, now that equilibrium is unbalanced, so what does the reaction do? Well, it will now convert some of its reactants into products to account for that loss where I removed something. So what's happening is our reaction is going to shift one way or the other to deal with that counterbalance, and that's a pretty cool thing. In this example, though, if we look at these pieces, is you may go through and say, well, doesn't that mean that my reactants will always equal my products? The amount of will be the same on both sides. Okay? In this case, yes, it will be. And as far as a chemist is concerned, where we're trying to make something, this is a horrible chemistry reaction, because this means the most product I could make would be half of the reactants I put in. So that's not a very good reaction. Okay, so what I might try and do is find a different reaction. Well, in finding a different reaction, what am I trying to find? What I'm trying to find is a reaction that the equilibrium has been changed. Okay? I can change where that fulcrum is located by changing the chemical reaction. So let's go through and say I place the fulcrum over here. How would that change my equilibrium? Okay, well, this longer arm, okay, this lever arm, now means that this red box is going to push down with a lot more force, which means I need a smaller amount of products to counterbalance that large reactions. So cool, I found a way to shift the equilibrium, where my equilibrium has now shifted. This shift in the equilibrium, though, is worse than I started with, though, because this is now producing even less products. So what I might do as a synthetic chemist is only run reactions that have fulcrums that are shifted way over to the product side of the equation. Because if that's the case, I now need a large mass to counteract that mass on the other side of our seesaw. For those of you that are kind of uncomfortable with this, because maybe you haven't done a seesaw before, is you can get two pens and take one pen and cross it over the other, and you can try and figure out how you could balance this out. So take one pen, lie it down, put another pen over the top of it, and you can use your fingers to try and level that out. How much force do you have to put down on one end or the other to make sure that the pen, the top pen, in this case our red pen, stays flat? Okay? That force that you're pushing down is effectively the amount of product or reactant in the solution at equilibrium. And that's kind of a neat observation. So we have a way to see, quote unquote, these things in the real world. Okay? We can also do this with two divided chambers. These divided chambers are going to have a trap door at the bottom. Okay? We're going to call this reactant and product. And that reaction can happen through that divided chamber. So if I'm going to start my reaction, what I'm going to start it with is just a bunch of reactants. So I'm going to fill up the reactant side. Okay? What happens to start the reaction? I can now wave a magic wand, and that trapdoor at the bottom now disappears. Okay? Well, if you've ever done this, what's that liquid in the reactant side going to do? Well, it's going to flow over to the product side. But now the instant it passes through that, it now becomes product. Okay? Well, how much product do we get? Where does this balance out? Okay? Well, it's going to balance out where the levels of reactant and product are again the same. Same deal with Le Chatelier. What happens if I add more reactant? Well, now the reactant has to drop down, the product has to go up to achieve that new balance, or that new equilibrium where they are evenly outlined. Okay? And that's the point of equilibrium. It's how do we do that kind of, how do we do that kind of transition through this? Okay? This example is a lot better than the seesaw for one big reason. One of the assumptions that people tend to make about equilibrium, largely because of the seesaw example, is that once we achieve equilibrium, the reaction stops. And that's not the case. Okay? The reaction doesn't stop. Product will still constantly be moving over to form reactant, and reactants will still constantly be shifting over to form products. Okay? In the seesaw, we don't see that. In this liquid sample, once we've achieved that balance, reactant or water is still flowing backwards and forwards through the bottom of that trap door. But the rate at which those things are moving is the same, and that becomes the key aspect for equilibrium. Equilibrium is explaining that we achieve this balance. That balance is now defined as the rate of the forward equaling the rate of the reverse. It is that relationship that now allows for all of the quantification, the mathematics behind all of these kind of expressions and thoughts. Those mathematics don't stress about, we will worry about, or you will worry about if you have to take more chemistry, and in particular, Chem 152. If you're only taking Chem 130, you just be like, hey, cool, I learned about equilibrium. Things are in balance. Okay? And things, when knocked out of balance, will always try to reobtain that balance. And that's equilibrium. The rate concept, what's happening with rates? Well, if we think about how those rates are going to change, let's go through and just fill up our chamber with reactants and look at our chamber of products with nothing in it. If we look at this state with nothing in my products, the rate going from reactant to product is probably pretty freaking huge. The rate going from product to reactant is, well, nothing. There is no product going to reactant because there's no product. Okay, so when we first start a reaction, the rates of those reactions are going to be different. As we give the reaction more time, that's when those rates start to level out. Okay, and that's going to address the first thing that affects our rates. Okay, we need to have that substance, concentration. Okay, we have to have compounds present. This, as far as chemistry, is marked in molarity or in pressure. Because most people get kind of bored with my chemical analogies, let's make this relationship advice. If you are trying to find a potential significant other long-term partner, and you are the only person left on the planet, well, the concentration is 1. To get another, or the concentration at that point is actually a lot smaller than that, because there's one person spread across the entire globe. Okay, so your concentration is effectively 0. If there isn't another partner, you don't find one. So the rate at which you find that partner decreases drastically. So what happens if we say increase the amount of people available? Well, now that there's more people, our concentration goes up and the odds of you finding a successful partner increase as well. And the speed at which you find that partner also increases because now you can have each of those interactions. Okay? What other things are going to contribute to this? Well, this is a fun one. The nature of the reactant. Okay? And before you start getting potentially bizarre with this, okay, what are we talking about here? Okay, what is the phase? How are these interactions potentially happening? If you are trapped, quarantined in your 5x5 office listening to this lecture, okay, the nature of the reaction is where you are allowed to exist, okay, your phase. If you're trapped in that 5x5 cubicle, you're not interacting with the world, which means it doesn't matter how many people are available in the entire space. There's a barrier preventing you from getting there. That's the nature of the reactant. Okay, so what we're referencing there is the phase. Okay, sometimes that's surface area. So if I'm looking at burning wood, okay, if I take a block of wood and light it on fire, it's going to take time to burn up. But what if I take that same block of wood and turn it into sawdust? It's still a solid. But if I now take that same mass of sawdust and light that on fire, it burns much quicker. Well, why? There's more surface area, okay, which is effectively changing the concentration. There's more surface contact between the solid and the gas oxygen, allowing for a faster burn. Okay, so a faster rate. So the nature of the reactant, thinking about phase and that surface contact. Okay, the next one's kind of an interesting one. Mechanism. How does this reaction proceed? Are you finding a potential significant other partner by putting on a blindfold and walking down the street and just grabbing people and being like, do you want to be my lover? Because I'm pretty sure that's not going to work out very well for you. Okay, so how are you going about finding that significant other? So the process by which it happens, okay, the reaction happens, can change the rate of the reaction. Okay, when we're thinking about our relationships, you may be going through and being like, well, I'm going to search at the gym, I'm going to search in the library, I'm just going to go hiking in the woods, and whoever I find is great because we both like hiking in the woods. Those are all different mechanisms behind that. But there's a thought process and an intelligence behind that. Chemistry doesn't have that. Chemistry is based off of what's known as collision theory. Okay? These are random particles smashing against each other. Okay? So if we're looking at the relationship love advice, you're just going into a crowded subway and bumping into each other and being like, dude, do you want to hang out? Okay? Depending on how you bump into that person, that you could end up with potentially a whole lot more lovers when you're put in jail. Okay, so you've got to be a little bit careful about that mechanism. Chemistry, they just smash and we see what happens. Temperature. Okay, temperature is directly related to the rate. The hotter things get, the more they move. If they move more, we increase the likelihood of making that interaction. Same works for relationships. Okay? If you just walk up and stare at someone, this is me staring at you. It's kind of creepy. So what do you need? You need a little bit more motion, like the movement of your mouth, expressing words, okay, making that conversation. If things are frigid, you're not going to move much and you're just going to be stuck there. Okay? So chemistry is doing the same thing. We need that motion. It's not a talking, but it's just more motion increases the odds of causing a reaction to happen. And then lastly, the extra fun one. You ever have that friend go, hey, you know what? I know somebody that you would really get along with. Okay? That's a catalyst. Okay? In theory, in the relationship system, it's the same deal. They aren't there to participate in your relationship or that budding relationship. They're there to make that connection and then they step away. Okay? That's what a catalyst would do. Okay? The catalyst is never consumed in the reaction. Okay? So if we think about that praying mantis style, hey, these two people would be great together. Let me introduce you, and then you kill the person that introduced you to that other one. Like that would be bad. Okay? Your friend still gets to run around and potentially wreak havoc in other people's relationships. Okay? That's what's happening with our rates when it comes to equilibrium. So now that we've had that little fun, we could go back to our chemistry and look at our equilibrium with our acids and our seesaws. Okay? Where this gets defined is in a term known as our equilibrium constant, K. It's a constant because it's always going to achieve the same balance. If I increase the products, the reactants will increase to counterbalance that increase in products. Okay? We could establish this relationship any way we wanted. We could have done it as reactants over products. Okay? Why did we pick products over reactants? Because P is a cooler letter than R. I don't know. That's just the way it is. Okay? So that is our defined expression. It's the concentration of our products over the concentration of our reactants. So we could come up with some K values for an individual reaction. So let's take an example. Let's look at the lower left fulcrum. Let's not look at that one because it's silly. Okay? We said our reactants are blue. If we looked at this fulcrum, we're probably looking at a large reactant and a very small product. Again, where that fulcrum is, I have to put a lot of weight on the smaller side to keep that pen in balance. Okay? In this case, if I looked at my K, that's going to be however many products we have, a very small number, over how many reactants we have, a very large number. This is going to result in a K that is very small. Okay? And in particular, it should probably be less than 1. Okay? What does that mean? Well, for scientists potentially looking at synthesis reactions to build something, that's probably not going to be a good reaction for me to go through and run, because I don't produce a lot of products. Okay, so why would we see reactions like this? Well, as we go through to study things, we're going to find and define these equilibrium constants so we can go through and understand the world around us. That's the point of it. Okay, so how could we use that back with our two substances down below? Okay, well, we have HCl and HC2H3O2. Because I know you've already watched the acid-base video, because that was the one that come before this. I know that you've spent the time to not memorize the strong acids like I told you to not do, and you would say that the HCl is a strong acid. Because it is a strong acid, it completely ionizes, which means it goes to form only products. Whereas the HC2H3O2, since it is not a strong acid, would be a weak acid, which means it does not form a lot of products. So HC2H3O2 would probably be looking at a K that is very small, okay, a number less than 1, because we're going to have a lot of reactants and not a lot of products. What happens if we shifted our focus, say, over to the fulcrum on our right? Well, on the right, now we've got a very large product concentration and a very small reactant concentration. What happens to our K value now? Well, our product concentration is large over our reactant concentration being small, and we would end up with a very large K value, a very large K number. That number would very likely be much larger than 1. What does that mean? We're favoring a lot to our products. HCl, as a strong acid, is likely to have an equilibrium constant that is very large. Okay, so what I want you to understand is the balance between these individual chemical reactions have identified equilibrium constants. Those constants would be things that you would look up and manipulate if you needed to. For the sake of this class, I just want you to be able to acknowledge what that dynamic is between our reactants and our products. I also want you to be able to consider what's going on with our rates and how those rates could potentially affect our equilibrium. Okay, so with that, we have a phenomenal, awesome ending. I'm throwing confetti. There's fireworks going off in the backyard, because this is the last lecture of Chem 130, and it is now ended.